Hello, good day. Lecture video. We will continue our discussion in in chapter 1, which is entitled Computer Arithmetic. We are now in part 3C. Okay, let me go to the slide. So this is our topic is all about uh, introduction to floating point arithmetic. So as you can see here, computers store numbers and perform computations. Could surprise the beginner. So in Python, as you can see, if you type the quantity of square root of 3 raised to the power of 2, the result will be 2.999 up to this one, 96, where the 9s here are repeated 15 times. So if you want to try it, then you can see that if you type this one in Python, you will have this number. So let me try it. So first is, let me go to my IDLE. Okay, so for example, we have let's import the math function. Import math, this one here, from sorry, let's say from math import square root. Okay, so let's have square root. Let's see, square root of 3 raised to the power of 2. So no, not 2. Okay, so we have 3 here, not 3, sorry. Copy. Okay, raised to the power of 2. Let's say we have 2.99, and these 9s here are 15, repeated 15 times. So this is clearly show that there is some errors in representing this number. So we will discuss this problem in more detail in the next section. So what happens here? It says that only finitely many numbers can be represented in a computer. Okay, so this means also that a number represented in a computer can only have a finitely many digits. So even if your computer is a 64-bit has a 64-bit operating system, or if you are using the fastest computer which was made in China, then to represent those numbers, you can only have a finitely many digits. Okay, so it will end. So what we'll do here is, therefore the numbers that can be represented in a computer exactly is only a subset of rational numbers. So anytime the computer performs an operation whose outcome is not a number that can be represented exactly in the computer, so there are numbers that cannot be represented exactly, so we will use approximation. So this let me exit that one. It says here an approximation will replace the exact number. So this is called the round-off error. So this is an error produced when a computer is used to perform real numbers number calculations. So maybe the computer can represent 15 digits or 8 digits. It depends upon the computer. So if you are using a calculator, so if you look at the display, so maybe the calculator can perform up to, let's say, 8 significant digits or 6 significant digits, depending on the calculator. Okay, so depending on the machine. So this is the the general model for representing real numbers in a computer. So this is what we call the floating point representation of real numbers. So if you have a real number x, you can represent this in this form for any base. Since our computer today uses only 2 digits, which is 0 and 1, so our beta here will be 2. Some computers uses 16 as the base, and as I recall, some computers also use 8, and some are uses 10 3 also. Okay, so anyway, when we try to represent a given real number x, we will use the binary system, or when beta is equal to 2. Okay, so our s here is design, and it takes only 2 values, which is positive 1 and negative 1. And e here is what we call the exponent, which has a bounds, L and E. The lower bound is L, the upper bound is U. And this part here, point a sub 1, a sub 2 up to a sub t, is what we call the mantissa. Okay, and beta here is what we call the base. And finally, our t is the number of digits, or the precision. Okay, so please remember this formula on how to represent given real number x. Okay, so next, let's have a note first before we are going to give an example on how to write a given real number x to represent a, what you call this one, a number in the computer. So note number 1 in the floating point representation 1, this one here. Okay, this floating point representation, if we specify the exponent e in such a way that a sub 1, this one here, okay, the this is the fractional part, so meaning this is the tens, hundreds, thousands, so this is the tens. So a sub 1, if we specify that a sub 1 is not equal to 0, then the representation is unique. Okay, so we need not to, what you call this one, to prove this one, and we just accept this result. If a sub 1 is not equal to 0, then that number is called a normalized floating point representation of the number x. Okay, if a sub 1 is not equal to 0. So for example, if our beta is equal to 10, if you have the decimal number, so if you are given 0.012, this one here, then if we write it in normalized floating point representation using base 10, then you can write it in this form. Okay, 0.12 times 10 to the negative 1. So we will not use this notation here, or this one, because it says that the a sub 1 must not be equal to 0. So if a sub 1 is not equal to 0, then that representation is what we call a normalized floating point representation. Okay, so the correct answer is this one. Okay, because 1 here is of course not equal to 0. Second note is a floating point number system within a computer is similar to what we have just described, with one important difference. Every computer has only a finite word length and a finite total capacity. We know that already, uh, since a computer uh, cannot what do you call this one, cannot represent in an infinite representation of a given number or a letter. Okay. And also we know that the total capacity of a computer is finite also. If you have a 500 gigabyte computer, then if that is full, then you cannot go beyond the total capacity. So it says here only numbers with a finite number of digits can be represented. Also here, a number is allotted only one word of storage in a single precision mode. For example, if you are given a number 5, then there is an equivalent word in the computer for number 5. It depends upon what type of operating system you are using. If you are using a 32-bit operating system or a 64-bit operating system, then the representation of that number in that system is different from the other system. So please do remember that there are computer. For me, for example, let's say, let me check my computer. For example, this one here at the bottom, I don't know, in the Windows operating system, you can right click the my computer and then go to the properties, maybe properties, I forgot, and then check it if the what type of operating system your computer is all about. So for me, I have here a 64-bit operating system. So there are computer that uses 32-bit operating system. So if a given number, example, if you have 20, and then in the 64-bit operating system there is an equivalent word or word in that number in this operating system, but it will be different in the 32-bit operating system. So anyway, there are many other computer that exist today. Maybe in a calculator it will have a different representation. So it says here also a number is allotted only one word of storage in a single precision mode, 2 or more words in double or extended precision. So as I've said, if you are using a single precision mode, you are using a 32-bit operating system. So if you are using a double precision mode, then you are using the 64-bit operating system. There are other what do you call this one, OS type that are in existing today. So anyway, the most common is the double precision mode, which is a 64-bit operating system. In either case, the degree of precision is strictly limited. Clearly, irrational numbers, it says here, irrational numbers cannot be represented, nor can those rational numbers that do not fit the finite format imposed by the computer. So furthermore, numbers may be either too large or too small to be representable. But there may be an errors that will come out later after, let's say, it will be what do you call this one, true if only to up to 8 digits or maybe 15 digits. So let's discuss that one later. Anyway, the real numbers that are representable in a computer, those numbers are called machine numbers. So since any number used in calculations with the computer system must conform to the format of the numbers in that system, then of course it has a finite expansion. So numbers that have a non-terminating expansion cannot be accumulated precisely. Moreover, a number that has a terminating expansion in one base we have a non-terminating expansion in another. So in the last sentence, it says that if for example 0.10 in base 10, it has a finite terminating expansion, but in another system, uh, the, the result will be a non-terminating expansion. Okay, so anyway, let me uh, write that as an example here. Let me open my open board. For example, here, uh, 0.10 or 1 over 10 in base 10, as you can see, it has a terminating expansion. It ends at 0. But if you convert this number, which is in base 10, to a binary number, it will have an infinite expansion. So you can write this one as 0.00, let's say 1 1 0 1 0 1 0 0 1 1 0 0 1 1, and so on and so forth. 0 1 1 0 0 1 1 0 0 1 1, and so on. Okay, so if you will not believe me, then you can try to convert using our previous discussion on how to convert a decimal number to a binary number. So I guess that topic is in chapter 1 part 3b. Okay, so let's sign this one first. So this is what it says in this last sentence. Okay, terminating expansion, we have a non-terminating expansion in another case. So okay, let's proceed to our discussion. So don't forget that this is the general model for representing real numbers in a computer. Okay, for this is what we call the IEEE 64-bit floating point representation. This is the same as you can see here. This is the same as in the general model, where, as you can see, we replace beta to be equal to 2, and then we move, as you can see here, we move 1 point here. Okay, so we have our a sub 1 now is equal to 1, and then this number here, the quantity of negative 1 raised to the power of s, represents, if you analyze it, it represents the positive number and the negative number. So if s is 0, we have a positive number, and if s is 1, then we have a negative number. So why do we have to represent a given number into this form? Back in history, in 1980s, a working committee of the institute, this one here, Institute for Electrical and Electronics Engineering, or IEEE, established a standard floating point arithmetic system for computers that is now known as the IEEE floating point standard. So what happened before? Notice in if you have a manufacturer in, for example, in America, you have a manufacturer of a computer in Russia and China, they have also a manufacturer of a computer. Then each manufacturer develop their own internal floating point number system. So what happened before is that if a particular computer made in USA, or if the other computer made in Russia, or other computer made in China, they have different internal floating point number system. Then a given um, number, for example, let's focus on a number. Example, if you have a number, real number 20, it may have a different representation in a computer made in USA, and a different representation if you are using a computer made in Russia or made in China. So this committee decided to create the standard floating point representation of a given number. So what happened also before is that there is an inconsistencies in numerical results in moving code from machine to machine. So this is the reason why they standardize in representing a what do you call this one, a number uh, that today that we are using. Okay, so this is now the uh, standard model on how to represent a uh, given number. Okay, so well, anyway, there are some comments here. This, as you can see here, we have if s here is 0, then that number is positive. If s is 1, then that number is negative. Okay, and also if notice also that since we are dealing with computers, our beta here, let me expand this one, our beta here is 2 because we are using the binary digits. Then since we are going to normalize the given floating point representation of a number x, then the first digit after the decimal point has to be 1, as you can see here. Okay, it cannot be 0. The reason for that is based on our definition, where's that one, definition of the normalized floating point representation of a number x. It should be unique. Okay, so the first this one e sub 1 here must not equal to 0. Okay, so that's the reason why there is a 1 in the formula. Okay, formula number 2. So that's why we write x as a decimal number starting at 1 in 2. So even though precision t is equal to 52, this is by, if you look at our general model, t is what we call the precision. Okay, we are able to access up to the 53rd digit, a sub 53. Okay, anyway, also we have some comments here. The bounds for the exponent are from 0 to 2047. We will discuss that later. Why is it that the upper bound is 2047? So let's focus on the exponent. We have 2 to the e minus 1023. If you look at our definition, we have, it should be 2 to the e. So why is it that uh, there is a negative 1023 in the exponent? Okay, so it says here that where's that one? This one here. But first, let's discuss why we have e to the negative 1023 as the exponent in the representation 2, as opposed to simply e, as I've said before. So notice that if the smallest number exponent possible was is equal to 0, then the smallest positive number the computer can generate is this one, 1.00 and so on, can base 2, which is certainly equal to 1. And certainly we need to computer is less than 1. So notice also that we have to represent those numbers that are less than 1. So this is the reason that we have to shift the exponent to this form, e minus 1023. And this exponent is what we call the bias exponent in the representation 2. And the bounds for the bias exponent is this one here. Okay, anyway, we will understand that one later after making a diagram. So let's proceed to the diagram. Okay, so this is the, notice that in our discussion, this is a 64-bit floating point representation. So in my case, I am using a 64-bit operating system. So look at this one. So here is the scheme that illustrates how the physical bits of a computer correspond to the representation above. So each cell in the table below, numbered 1 to 64, corresponds to the physical bits in the computer memory. Because the language of the computer is represented by 0 and 1. So if you have a 64-bit operating system, so for example, you have these boxes here. The number 1, this one here, is the sign bit. And it takes two values, which is 0 and 1. As I've said before, 0 represents positive number and 1 represents negative number. Okay, so so this is the first bit, and this is what we call the sign bit. Okay, so next is, look at the blue bits, this one here. The blue bits from 2 to 12, and as you have noticed, there are 11 boxes here in blue color. So from 2 to 12, we have 11 boxes. These blue bits represent the exponent. Okay, exponent e, not e minus 1023. And there are 11 bits here. Okay, so one can generate the integers from 0 to 2 to the 11 minus 1, which is equal to 2047. So this is the reason why in the comments below, this one here, where are you, this one here, the bounds is from this one, the upper bound is 2047. Why is it that you have to subtract 1 in the 2 to 11? Why is it that this is 2 to the 11? If you are studying combinatorial mathematics, in the first box 2, okay, the blue bits here, the box 2 stores two numbers only, 0 and 1. And for box 3, another, we have 0 and 1, box 4, 0 and 1, box 5, 0 and 1, and up to box 12, 0 and 1. So there are 2 to the 11. So why do we have to, what we call this, to subtract 1? Notice that this box here, which is a sub 1, this is our a sub 1 point. This is sign bit, this is a sub 1. Notice that since we are using we are representing the normalized representation of a number, it is in normalized form, a sub 1 cannot be 0. So we have to subtract 1 here. Okay, so this is the reason we have 2 to the 11 minus 1. Okay, and as you can see here, the smallest and the largest values for E is 0. So we have 0, 0 here. This one, this representation in binary is, in decimal we have 0. And the largest number is this one, 1, 1, 1, 1. Okay. And we know already how to convert this binary number in a decimal number. So this is how you are going to convert this number to this form. We already discussed that one in I guess in chapter 1 part 3b. Okay, so after simplifying, you can get 2047. Anyway, this is very familiar, which is in calculus 3. So this is easy to convert. This one, we have summation of geometric series, I guess. Anyway, if you are doubting that this is equal to 2047, then you can try to use your calculator. And also from box 13 up to box 64, the real bits are, there are 32 of them. So since this all in all we have 64, so we have 64 minus 12 is, we have 52. Okay, and box 13 up to box 64 stores, let me skip that one first. Store the digits a sub 2 through a sub 53. So meaning to say, if you look at the IE 64-bit floating point representation, this digit for a sub 2 up to a sub 53, this is what we call the mantisa. Okay, so from a sub 2 to a sub 53, so this red box here. Okay, so let's try to do this example. Example 11. Okay, find the floating point representation of 215.4896. So remember that we are trying to convert this number to a binary number. Okay, since we are discussing about computer arithmetic. Okay, so let's try to solve this one. Convert this to a normalized what do you call it, a 64-bit floating point representation of this one here, this number. Okay, so let me open my open board. Let's have another page. Try this one first, and then let me open my com. Okay, solution. Solution. Recall. So let's recall our number. Our number is where are you? 215.4896. 215.4896. 4896. So this is the solution. Okay, we can check. We can check that 215 is equal to, remember in our previous discussion, if we are going to convert this decimal number to a binary number, we have to separately convert the integral part and the fractional part of this decimal number. So 215, let's try our scratch here. Let's scratch. Okay, so let's divide 215. So you can review our previous discussion, our previous video to, I guess, chapter 1 part 3b. Okay, so we have 215 divided by 2. Our base is 2. So 215, let me get my calculator first. So 215, the quotient is 215 divided by 2 is 107, and the remainder is 107 times 2 is 1. Remainder is 1, and then divided again by 2. So 107 divided by 2, our quotient is 53. Okay, 53 times 2, 106. So our remainder is 1 again. Divided by 2 again, up to 0. 53 divided by 2, our remainder is 26. 26 times 2. No. 26 times 2. 52. Our remainder is 1 again. Okay, so divide 53 divided by 2 is 26. 26 times 2 is 52 minus 1. So 26 divided by 2, we have 13. Our remainder is 0. Divide 2 again. We have 13 divided by 2 is 6. Remainder, quotient is 6, and then remainder is 1. Okay, divide 2 again. We have 3 here. No, we have C sub 4. Sorry, this one is C sub 4, C sub 4, C sub 5, C sub 6. So 6 divided by 2 is 3, remainder is 0. Divide again by 2. We have quotient is 1, and then remainder is 1. Finally, the last one, divide 2, we have quotient is 0, remainder is 1. Okay, so 215 in binary, we have 1 1 sorry, 1 1 0 1 1 0 1 0 1 1 1 in base 2. Okay, so n decimal, our decimal is 0 point, we have here 0.4896. So how do we represent uh, the fractional part? Okay, for the fractional part, this is the integral part here. We have integral part, integral part. So for the fractional part, fractional part, we have 0.4896. So what have we done before? We have to multiply 2 and ignore the integer part. So multiply by 2 times, okay, 0.4896 times 2, we have 0.9792. Okay, and this is our, if you recall, documents. Where are you? This one here, maybe this one, page 5. Am I right? This one. Where are you? Not this one. How about this one here? This one. Oh, sorry. This one here. Okay. So we multiply. Let's hide that one. Let's open our latest discussion. This one here. Okay. This is B sub 1. Let's use another notation. Multiply again by 2, 0. Maybe let's try to, what do you call this one? Let's try to have a finite representation. Let's replace this one here, the fractional part, by a number which is which can be represented in finitely. So let's try maybe 375. Okay, and let me change my slide also. Okay, let me change my slide. I guess this is 9 8, no, where are you? 4896. 4896. Let's replace this one by 375. 375. Okay, let's run this one. Okay, so let's continue this one. Okay, so let's replace this to point 375. Okay, so that we will have a finite representation of that number. So 0.375 times 2, so 0.375 times 2, we have 0.75. So this is our b sub 1, b sub 1, this one here. Again, we multiply by 2 times 2 times 2, 1.5. So this is our b sub 2, that one. Multiply again by 2, we have 3. So 3 here is 3.0. 3.0, we have, let's have a bubble thought here, bubble thought. So the answer is 3.0. So let's we know that to represent 3 in a computer, we have, the answer is 1. So this is 1.0. Okay, so our b sub 3 is 1, this one here. Okay, so let's now proceed. 0.375 is equivalent to 0.011 in base 2. Okay, so this one 0.11. Okay, so after this we have then 215 0.375 is equivalent to 110 10111.011 in base 2. Okay, but this answer here is not the normalized floating point representation of the number x, so we will write it in this form. We have this one here. Let's move the radix point 1 2 3 4 5 6 7. Okay, 7. So we have 1.10111 times base 2 times 2 to the 7. We have here 1 2 3 4 5 6 7. Okay, so this is the normalized floating point representation of the given number. Okay, where 1.1011 times 2 to the 7 is the normalized floating point representation of the number. Okay, so this is in our previous discussion. As you can see here. Okay, this one, where are you? This one here. Okay, so our one, this is equation 1. So if a sub 1, okay, is not equal to 0, we have a normalized floating point representation. So we will now write our answer in terms of 1 point, this one here, in terms of equation 2. So let's write this in equation 2. So let's try to move it somewhere here. Now we rewrite this in terms of the representation representation 2. Okay, so 215.375 can be written as please do remember, in our discussion we have this form, -1 to the power of s. So -1 to the power of s, our s should be 0. Why? Because our number is positive. Okay, so next is where are you? This one, I'm sorry, this one here, 1 point something. Okay, 1 point something. So we have this one here, 1.103111 base 2 times 2 to the, so how you will represent this exponent, this exponent here, 2 to the 7 into e to the 1023. Okay, e to the 1023. So we have 1023 here, we have minus 1023. Okay, so what should be the number here, so that the not the product, the result equals 7. So for me, I guess let's have another color here. Maybe let's try green. Is this true? 1030. Okay, because 1030 minus 1023 is equal to 7. Okay, so this is now the normalized floating point representation using equation 2. Okay, equation 2. So let's put a point there, and then to write it in this form, in this box here. Okay, so to write it in the box, so we have to represent 1030 in a binary number. Okay, so our E here is the blue bits. Okay, the blue bits, and 13 up to 64 is our mantissa. Okay, so anyway, let's convert our exponent to a binary number. So let me write it here. Since 1030 is equal to, again, let's try to solve it in our scratch. Let's try to solve it somewhere here. We have 1026. Okay, we divide 1026. No, 1030 divide by 2. So 1030 divided by 2 is 515. The quotient is 515, and C sub 0 here, the remainder is 0. Okay, so divide this one again by 2. So 515 divided by 2, our quotient is 257. 257 times 2 is 514. So our remainder is 1. So divide again by 2. 257 divided by 2 is 128. So 128, saying our remainder is 0. Okay, divide this one by 2 again. So let me review this one. Did I make a mistake? We have 215 divided by 2, 107. Okay, that's correct. 128 divided by 2 is 64. 64, our remainder is 0. Divide 2. 64 divided by 2, we have 32. Our remainder is 0. Divide 2 again, we have 16. Our remainder is 0 again. And then divide 2, we have 8. Our remainder is 0. Divide 2 again, we have 4. Our remainder is 0 again. Divide 2, our remainder is 2. Our remainder is 0 again. Last, we have remainder is 1. 0. Remainder is quotient. Sorry. Quotient is 1. Our remainder is C sub 9 is 0. Am I right? Okay. And lastly, we have quotient is 0, remainder is 1. Okay, so meaning to say, sorry, that one. How do we represent 1030? So this implies that 1030 is 1, how many zeros? uh, 1 2 3 4 5 6 7 8, 8 zeros. 1 2 3 4 5, sorry, 1 2 3 4 5 6 7 8, and then 1 0. We have 1 0 in base 2. Do you think this is correct representation? So we have here the first, this is a sub 0, a sub 1. So this could be 2 to the 1. Let's check. 2 to 1 times 2 to the 1, and then also the last one, because from this digit 0 was this one 0 0 0 0, we have 0 times a number is 0, so plus, so this is 10. Okay, 2 to the sorry, this is 1 times 2 to the 10. Okay, so let's try to evaluate it. So this is 2 plus 2 to the 10. 2 to the 10, 2 to the 10 is 1024. Sorry, 1000. Oh my god, what happened? This is 0 0 1 2 3 4 5 6 7 8 9 10. What happened? 1024. Did I made a mistake here, which is 1024? So we have 1026. Okay, sorry for this one. So where did I made a mistake here? Did I make a mistake here? 1030 divided by 2 is 515. Quotient, remainder is 0. Let me check this one. 515 divided by 2, 257. Remainder is 1 here, remainder 0. So did I make a mistake somewhere? I'm sorry for this one. Let me pause the video. Oh my goodness, where did I make a mistake? Did I make a mistake somewhere? 515. I'm sorry, I'm going to cut the video first. I'm going to cut the video and then check the division, okay, first. So let's hide this one first, and let's okay, let's continue our video. Okay, so let's continue. I made a mistake somewhere here. Did I start recording? Okay, anyway, I hope that this will be recorded. I made a mistake somewhere here. This one, okay, this one here, this should be 1. Okay, so let's erase this one. Let's erase this. This should be, okay, 1, because 257 divided by 2 is let's put somewhere here. Let's put a 257 divided by 2 is 128, and this is 256. Okay, so the quotient is 128 and the remainder is 1. Okay, so let's move again. So we have to replace, sorry, this one, this should be 110. 110, and we have to include somewhere here plus 1 times 2 square plus 1 times 2 to the 10. Okay, so this will be 4. No, let's go back. This is 2 to the 1, this is 2 square plus 2 to the 10, and then erase this one. Okay, plus 4 plus 1000, so 2 to the 10, 1024. So this is 1030. Okay, so this is now the representation of the binary representation of this decimal number. So 1 1 2 3 4 5 6 7 7 zeros. So 1 1 7 zeros, 1 2 3 4 5 6 7, and then 1 1 0. This one here. Okay, so let me count. 1 2 3 4 5 6 7 8 9 10 11. Okay, there are 11 numbers. Okay, so therefore, since 1030 is equivalent to that one, okay, the bit by bit representation is okay. So let's create a boxes. So let's recall this one, this box. Let's create this box. For the first box, we will put what do you call this one, 0, since it is positive. Okay, so let's create a box here. Let's have this color red, this one here, red one. Let's create a box. Okay, let me somewhere here. Okay, so for the first box we have 0. Okay, for the second box is our exponent, this one, 1030. Okay, this one here, this one. So let's make 11 boxes. So 1 2 3 4 5 6 7 8 9 10 11. Okay, so we will write the blue, we will use the blue color. So we have 1 0, how many zeros? 7, 2 3 4 5 6 7, and then 1 1 0. Okay, after this we have the mantisa. Okay, so the mantisa is this one here, 1 0 1 0 1 1 1 0 1 1. Okay, how many? 1 2 3 4 5, 6, 7, 8, 9, 10. So let's put 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Let's continue up to this point. This last box here, and then let's put dot dot dot. So let's use color red. Okay, this is the Matisa. This one here, Matisa 1011. This one. Okay, so let's put color red. We have one. No, maybe we will use color, let's say green. 1 0 1 0 1 1 1 0 1 1, and then after this last digit 1 here, put all zeros somewhere here. So meaning to say there are as you recall, there are 52, then minus 10, if there are 10 digits are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the remaining is, we have 42 zeros. Okay, 42 zeros. So let's try under this color here, black one. We have 0 up to and so on to the last digit is 0. So this is now the bit by bit representation of the number. What number? Okay, the number 5. Where are you? 215.375. Okay, 215.375. We have 0 1 0 0 0 0 0 0 0 1 1 0 0 1 0 1 0 1 1 1 0 1 1 0, and so on, 0 0. So this is the bit by bit representation of 215.375. If you are using the 64-bit floating point representation of this number, if you are using a 32-bit, that's a different story, because you are using 32 boxes only. Okay, if you are using 8-bit operating system, then you are using the boxes are 8 only. Okay, if you have the extended, then maybe those high-speed computers uses maybe 64, after 64, 32, 64, 64 times 64, 64 plus 64, 8, maybe you can use 1 to 8 operating system, if that's possible, if you have that kind of computer or laptop. So the presentation will be different from the other computer to the other computer if you have different operating system, type of operating system. So for me, I am using a 64-bit operating system, therefore 215.375 is the representation is just like this one. Okay, so I guess that's all for this discussion. I hope you now know how to convert a decimal number to a 64-bit floating point number. Okay, so let's go back now to our slide, this one here, this one. Let's hide this one here. Let's hide. Okay, so for our next topic, we have the special cases. We have the 0, infinity, and the none or not a number. We will discuss this one. Okay, and then also representation of integers, and the last one we have this one, chopping and rounding, after this one, so maybe let's end with this discussion first. Okay, so anyway, let's escape and then let's okay, before we this topic, special cases, 0, infinity, and none, I forgot to check or to use our Python uh, to check the if this number 215.375 has a command which is the same, the result which is the same as our computation or hand computation. So what I will do here is to open my Anaconda navigator. So I will open my Anaconda navigator, and then let's put a code, a series of code to check our result. Okay, our result, this one here, if this is correct representation, this one of 215.375. okay, so this is the code. Let's wait for the Anaconda navigator to pop up. So where are you? Let's hide, maybe let's hide this one first. Okay, this one. I'm going to open my spider. Okay, I'm going to launch my spider. After this, this is the code. Where are you? Okay, this one. Okay, I already typed the program. This is a series of code. It says here import struct. I'm going to call the package struct and then define the function. Let's replace this function as float to bin, and then let's write also this one here. Replace, we have float. Okay, since we are getting the real number, our real number is there's that one, 215.357. okay, am I right? 375, sorry, 375. okay, so I'm going to save it here, and then I'm going to run. Oh, there's problem. Let's this one here. Okay, maybe let's delete my count first. Okay, quit. Okay, so this is, I think we are correct. The first bit, which is 0, represent the positive number. We have the 11 bits. We have 1 0 0. There are 7 zeros, 1 7 zeros, and 1 1 0. Okay, so let me have here 1 1 2 3 4 5 6 7 7 zeros and 1 1 0. For the mantisa, we have 1 0 1 0 1 1 1 0 1 1. Okay, let's try mantisa. Somewhere here we have 1 0 1 0 1 1 0 1 1. Okay, after 0 1 1 we have a series of zeros. Okay, there are 42 zeros after this digital 0 1 1. So I guess we are correct. You can zoom out. Okay, you can zoom out. You can use you can zoom your the lecture video if you are watching this. So I guess we are correct. Okay, so now I am confident So let's go back to our slide. So as you can see here, let's try this one. Okay, for our special cases, we have 0, infinity, and none. Okay. After discussing this one, I'm going to give a problem set, and then let's have one more discussion. Let's skip this one first. I'm going to open my camera. No, not this one. This one. Where are you? This one. Okay. Okay, this one. Before I am going to, after discussing this topic, let's differentiate between a 32-bit computer system or operating system and the 64-bit operating system. Okay, let's try the difference between the two. Okay, before I'm going to give you a problem set. Okay, let's proceed in special cases. The floating point arithmetic for two zeros, since we have positive 0.0 and negative 0.0, they have a special representation. In the representation of 0, all exponent and mantissa bits are set to 0. The sign bit is 0 for negative, positive, and 1 for negative. So this is the positive 0, and this is the negative 0. So look at the difference is this one, the sign bit. Okay, and then it says here, when the exponent bits are set to 0, we have e is equal to 0, and thus we have this one, negative. Okay, let's skip this one first. Where are you? This one. Okay, so we have negative 1023. So this arrangement, all exact exponent bits set to 0 is reserved for this one, two numbers, positive 0.0 and negative 0.0. So this one here, negative 1023, for the 64-bit operating system, this number here, it will represent the smallest smallest machine number. Okay, and also for subnormal numbers like none, infinity, and also for infinity. So this is how you are going to represent for positive infinity. We have for positive, we have the sign bit must be 0. For negative, we have is 1. And then the difference is 1, all ones. Okay, so this must be 1. This one here, all ones. Okay, the 11 digit must be all ones, and also this one here, and the rest is 0. Okay, so sorry for this one, I made a mistake again. So let's close this one here, let's close that one, and let's where are you, this one here, let's close this, and let me open my text studio to edit this one here. This should be 1. Okay, for minus infinity. Okay, so where are you, this one, no, this one here. Okay, all ones, okay, all 0. So this one, this should be sorry, where are you, all ones, all 0s. Okay, blue, red, this one here, it should be 1. Also this should be 1 also here. Okay, so let's run this one. Maybe we can have 0 there. So that's how you are going to represent a special number, special case. So this one, okay, this is the right one for the 0 and infinity. Okay, so in conclusion, notice that even though we have this inequality in representation 2, the IEE 64-bit floating point representation, when it comes to representing non-zero real numbers, meaning to say non-zero is negative, we have also positive, we only have access to exponents in the following range. This one. This is because there's a reason for this one. Okay, and as I've said before, the smallest positive real number that can be represented in a computer is this one here, 1.00 times if e is 0. Okay, so this is number here is equivalent to this form, and the largest is this one here. Okay, so this is easy to calculate. So we have 1023, this one here. Okay, so anyway, 0.8, this is a very big number. Imagine we have a decimal digit, we have 10 to the 309. I don't know what kind of number is this, maybe septillion or something, I don't really know. Anyway, I will try to answer this inequality here after differentiating the difference between 32-bit operating system and the 64-bit operating system. So let me read to you this slide, this sentence here. Two more sentence, and we are now in the problem set number 3. During a calculation, if a number less than the smallest floating point number is obtained, meaning to say it is smaller than 0.2 times 10 to the negative 37, then we have an underflow error. Okay, if it is bigger than 0.18 times 10 to the 309, then we have an overflow. Okay, this is what we call overflow. Okay, so in the succeeding discussion, I will try to illustrate this one in the Python. In Python, what do we mean by underflow and overflow? Okay, so let's see if a particular if a certain computer has a problem in representing a non-zero real number which is smaller than 0.2 times 10 to the negative 37 and 0.18, which is larger than this one, 0.18 times 10 to the 309. Okay, let's try to illustrate this kind of error later. Okay, so anyway, this is your problem set. This problem set is a toy model of for a normalized floating point representation in base 2. This one here, this representation, as you have noticed, we can access up to two decimal not decimal, 2 digits from the left of the radix point, a sub 2 and a sub 3, and our e here, our exponent is between negative 1 and 1, so meaning there are only 3 numbers, no? Negative 1, 0 and 1. Okay, Of course, we will not count the one half exponent, because of course we are dealing with in a when we say exponent, it should be in an integer. Okay, and you are asked to find all the machine numbers that can be represented in this model, and then convert the numbers to base 10. So after getting the numbers in this toy model for a normalized floating point representation in base 2, convert those numbers in base 10 so that we can understand. After that, you have to make a number line by hand, so in a pen paper or yellow paper, and then make a number line and plot those numbers in the number line. Okay, and so, and comment on how the numbers are spaced. So this is your um, problem set. So anyway, next discussion will be the discussion between the difference between the 32-bit and 64-bit representation of a given number. So there's not uh, much difference, but to give you an overview, this is the this is the model for, or the figure for the 32-bit operating system. So we reserve for the first box the first bit to be the sign, and then we will allocate for the exponent, we will allocate 8 bits, and then for the mantissa we will allocate 23 bits. So all in all, 23 plus 18 plus 1, we have 32 bit. Okay, so this is this is the 64-bit. So I already discussed this figure. Okay, so 52 for the mantissa, 11 for the exponent, and 1 for the sign bit. Okay, so this is how you are going to how we are going to differentiate between 32 and 64-bit. But let's have more examples in the next video. So anyway, thank you so much for watching, and I hope you will enjoy studying with me. I'm also overwhelmed with with this uh, this discussion, and I'm hoping that we all learn from this topic in numerical analysis. So see you in the next video. Thank you so much for watching. Okay, the discussion of this topic, representation of integers. I promise that I will be discussing the difference between the 32-bit and the 64-bit floating point representation of a given real number. But I recall that I made a mistake somewhere here. Okay, this mistake is very much needed in discussing the difference between the 32-bit and the 64-bit floating point representation of a given number. Well, anyway, as you can see here, in our previous discussion, we have this inequality. This is the bias exponent of the representation, floating point representation of the IEE 64-bit floating point representation. If you recall in the previous discussion, and as you have noticed, in this sentence it says that when it comes to representing non-zero real numbers, we only have access to exponents in the following range. So notice that it is less than 1. In the upper, we have 1024. Here we have 1023. And in the lower, we have negative 1023. In this one also, we have negative 1022. So it is 1 less. Okay, so what is the reason? I forgot to mention that those numbers in the endpoints will represent the, what do you call this one, the special number. Okay, this number, what is this one, this here, 0, infinity, and none. Okay, so this is the reason why we can access up to these numbers only. And also I also made a mistake here. I write it before in the previous discussion as negative 37, which in fact uh, it will be negative 307. Okay, so, and I also forgot to what do you call this one, to discuss why is it that this number here is this number here 2 to the negative 1022 is equivalent to this form. Okay, anyway, let's discuss this very important facts. So let me open my open board here, and then call this one, open. Okay, this one. So notice in the previous discussion, this representation is the IEE E64-bit floating point representation. It says here that the smallest positive real number, this one here, is this form, while this one here is the largest. So, okay, so notice that the fractional part is 0.0000. Okay, so this is the smallest. If you recall also in this discussion we have here. Okay, so let me go back and notice that in this expansion, in the fractional part, we write it in the normalized form. Okay, so although all these numbers here is 0, so this is the smallest. But notice in our previous discussion, so this is this one here, this, what do we call this one, illustration, explanation. Let's try explanation. Okay, so for the smallest number we have x negative 1 to the 0, we have 1.00 and so on. Okay, times 2 to the negative, sorry, where are you, negative 1022, this one here. Okay, this one here. So negative 1022. Okay, so since this is this one here is the fractional part, you can represent that one as 0 times 2 to the negative 1. Okay, so since we have a base 2, 0 times 2 to the negative 2. and so on up to 2 to the sorry 0 times 2 to the negative, let me check it, up to 52. Okay, negative 52. And as you have noticed, this is always equal to 0. 0 times a number is 0. Okay, this is always 0. So what remains here is negative 1 to the 0. This one here, this is multiplication. Okay, multiplication, this is 1. Okay, and here we have this one here, this one, let's have this color, let's say color blue. This one here we have 1 times 2 to the 0. Okay, so why is that? The exponent in the fractional part, will start at k is equal to 1, while in the integral part it will start at k is equal to 0. So if you remember the formula, let me recall that one, this one here, this formula, where are you, this one, I guess this one here. Okay, so it will start at 1. Okay, and for the integral part it will start at 0. So if you go back to this problem, where are you, where's that one, this one. Okay, that one, we have 1 times 2 to the 0. So remember in your high school mathematics, so for example, this one here, let's move it on the other side. If you have 1 point, sorry, so if you have example 2 point, let's try this color, 2.37. Okay, you can write this one as 2 plus 37 over 100. Okay, so this will be the same as this one here. You can write it as 1, okay, 1 times 2 to the 0 is 1 plus 0. Okay, so we have 0 because all these things here are 0. Okay, so what remains here is you will have 2 to the negative 1022. Okay, so that's the reason why this expression here is equivalent to 2 to the negative 122. So how do we get 0.2 times 10 to the negative 307? Okay, let me go to the Desmos calculator. Let's say Desmos scientific calculator. Yes, you have to click this one. Okay, so if you type 2 raised to the power of negative is the negative 1022, so as you can see, enter, so you will have 2.2 2.22507 2.22507 this will be this one here. Let's have this color. Let's have a bubble dot here somewhere. 2.22. Where are you? 507,386. 507,386. 386 times 10 to the 1. Where are you? Negative 308. 308. Negative 308. So what we will do here, this is approximately equal to, we can write that one as 0.2. Okay, you can move this one here, one decimal place, times 10 to the negative 307. Okay, so that's the reason why we have this expression here. Okay, for the largest number, for this one, so the largest exponent, we have to use this bound here. Okay, 1023, not 1024, because we reserve the other digits, the last point to 0, infinity, and none. Okay, so that's the reason. So how do we get this expression here? This is very easy. The largest would be all be equal to 1. Okay, the fractional part. So if you have this one here, I hope you will be able to get it. So we have largest number is x equal to negative 1 to the 0. We have 1.111 times 2 to the 1023. Okay, so actually the same method. So this one here is positive 1. Okay, positive 1. So times this one here, we have this is just like before this analogy. We can write this one here as 1 plus, this is 1 times 2 to the negative 1 for the first digit here. For the second, we have 1 times 2 to the negative 2. Okay, plus 1 times 2 to the negative 3, and so on and so forth, up to 1 times 2 to the negative 52. Okay, so we will multiply it by 2 times 2 to the 1023. Okay, so as you can see, we can simplify this one as 1 plus 1 half plus 1 over 2 square plus 1 over 2 cube, and so on up to 1 over 2 to the 52. Okay, times 2 to the 1023. So this is the same as this one here. Okay, so how do we get this number? This expression in the parentheses is equivalent to 2 minus 2 to the negative 52. So please do remember that uh, in the fractional part there are 52 digits all in all. Okay, so please remember that. Okay, so in the 64-bit 64-bit floating point number, so how do we express this one as this one, 2 minus 2 to the negative 52? So as I've said before, if I remember it correctly, in the geometric series, the formula for, let's have a recall somewhere here, recall this one, summation of a r to the I minus 1. I starts from 1 to n. We have a finite sum. This is a r to the 0 plus a r to the 1 plus a r to the 2 and so on up to a r to the n minus 1. Okay, so this is equivalent to a times 1 minus r to the n over 1 minus r. Okay, so this is the formula. You can recall this formula in calculus 3. Okay, so we will use this with a equal to 1/2. Okay, equal to 1/2. So we can write this one as summation of 2 to the 1/2, let's say 1/2 to the I minus 1, where I starts from 1 to 53. Okay, why is that? When I is equal to 1, we have, when I is equal to 1, we have 1 minus 1 is 0. A number raised to the power of 0 is 1. So we have the first term here. Okay, so for the second term, when I is equal to 2, 2 minus 1, we have 1/2. Okay, when I is equal to 3, we have 1 over 2 square. Up to the last digit, last term, we have 53 minus 1 is 52. Okay, so if we use let's say times 2 to the 1023. Okay, so if we use our formula, as you can see here, this formula, our a is 1. Okay, so we have, let's try to answer this one. This is a is 1, so we have 1 minus 1/2. Okay, let me make it clear. Let's make it bigger. 1 minus 1/2 to the our n is 53. Okay, and then 1 minus 1/2 times 2 to the 1023. Okay, let's simplify this one here. Let's simplify. So this is in the denominator we have 1/2. In the numerator we have 1 minus 1 over 2 to the 53. Okay, 2 2 to the 53 times 2 to the 1023. Okay, so what will happen here, we have get the LCD in the numerator, 2 to the 53, we have 2 to the 53 time divided by 1 times 1, so we have 2 to the 53 minus 2 to the 53 divided by 2 to the 53 is 1 times 1, so we have 1 here. Okay, so we have 1 half times 2 to the 1023. Finally, we can do reciprocal. So we have did I make a mistake somewhere here? We have 2 to the 2 to the 53, 2 to the 53 times 2 over 1. Okay, so we have times 2 to the 1023. So finally we have now not 25, this should be 53, sorry, 2 to the 53. So we can cancel out. Okay, so this is 52. Okay, so we have 2 to the distribute 2 to the 53 over 2 to the 52 minus 1 over 2 to the 52. So we can multiply by 2 times 2 to the power of 1023. And finally, we are almost done. So this is 2 minus 2 to the negative 52. Okay, times 2 to the 1023. Okay, so I think we are done. This is the same as this one here. Okay, so how do we get this number? So again, all you have to do is to use this calculator. We have, let's say, close 2 minus 2 to the negative 52, and then let's multiply it by 2 to the 1023, 1023, and hit the enter. So we have 1.7. Okay, 1.797, 1.797. Let's try it. Let's use the double dot. The double dot here, 1.797, 1.797, 693, 693, 693 times 10 to the 308, 308, sorry, 308. Okay, so look at our answer. We have 0.18. We have to use the normalized form. So we have here 1.0 point. Okay, you can move one place to the right. This one here. We have 0.0 179769313 times 10 to the 307. Okay, since you move to the right, and then you can truncate it, this one you can get this one 0.18 approximately. Okay, 10 to the 307. Okay, so I guess we we truncate it, so we have 309. We move one place to the right. This is 300. Okay, I'm sorry, should be 309. Sorry for that one. Should be 309. Okay, so since we move one place to the right, okay, so that's the reason behind these numbers. Okay, so and also I remember my mistake somewhere here. Notice this expansion, this one here, this expansion. If I remember it right, I may I made a mistake somewhere here, this one here. Okay, I think this one. Okay, the reason why we have to put -1 here is based on this analogy. Okay, so 2 to the 0 plus 2 to the 1 plus 2 to the 10 is equivalent to 2 to the 11 minus 1. You can use this argument uh, to have this expression here by using this formula. Okay, this formula, if you remember it right, this one. Okay, so you can use this one. Okay, so that's the reason why we have this one here, not the combinatorial something. I made a mistake in that discussion. Okay, so anyway, let's move now to where's that one. Okay, to differentiate, we are now ready to differentiate the difference between the 32-bit and 64-bit floating point representation. Okay, so let me have this one here, a new page. Okay, so this is the comparison between 32-bit and 64-bit. Okay, floating point representation. Okay, floating point representation. Okay, so for example, if you have this one here, we have 32-bit, and let's compare somewhere here. Sorry, we have 64-bit here, for example, 64-bit. Okay, so if 32-bit representation is same as this one. Okay, single precision. If you heard this word, single precision floating point numbers. In here we have double precision. Double. Why double? Of course, 32 plus 32 is 64. Okay. Floating point number. Okay. So the representation for the 32-bit, as I've said before, if you recall it in this one, hide this one. If you recall this diagram for the 32-bit, so we have for the first bit we put the sign bit. Okay, so this is for the sign bit, and then for the next 8 bits we have the exponent, and for the next 23 bits we have the mantissa. So that's why we have here in the double precision we have 52 bits in the mantissa. And if you recall in our discussion, this one here, our expansion, we have the exponent, we have 52. So because we are considering the fractional part only. Okay, so where are you? So this is the representation using the representation using a 32-bit. So we have -1, your number is -1 to the s. Okay, and then you will have here the what do you call this one, the 1 plus mantissa. Okay, so this is called the 1 plus mantissa times 2 to the e minus 127. So this is how you are going to represent the when you are using a 32-bit. And before, in the double precision, we have here -1 to the s, we have 1f the same times 2 to the e minus 1023. Okay, so just look at the difference. So when you are using the 64-bit operating system, this is much bigger, okay, than this one here. Okay, so as I've said, this is the graph or the figure for the 32-bit. Okay, so for the first box, okay, you will represent the sign bit. Okay, for the, okay, let's extend that one here. Okay, so for the exponent, bias exponent, okay, so this is the bias exponent e. Okay, and finally this is the mantissa. So we have f, okay, fractional part, f from 1 plus mantissa, 1 point f 2. Okay, so this one here. Okay, so from here, let's say we have 9 bits. Okay, and this is the radix point, and here we have the 23 bits. Okay, so this is the mantissa. So 23 plus 9 is 32. Okay, we have 1 here plus 8 equals 9. So the same is true for double precision. So the difference is quite simple. For this first bit, we have the sign bit, plus minus or 0 1, then the bias exponent E, and then after this is the f plus, no, the f from the 1 plus mantissa, this notation, this one here. Okay, so let's move it somewhere here. F from 1 plus mantissa, 1 dot f sub 2, and the difference is that from here we have 12 bits, and this is the radix point, and this is the 52 bits in the mantissa. Okay, so that's the difference between 32-bit and 64-bit. Okay, so let's have some comments here. Let's say some comments. Let's try this. Some comments. Okay, so the smallest number, okay, we know that in what do you call this one, let's put 1 here. The smallest number in double precision, smallest number, we already know that this is this one here. Let's open this one. This is the smallest number in the double precision, and we know the computation already. Okay, so this is x negative 1 to the 0 1.000 base 2 times 2 to the negative 1 0 to 1 1023. Am I right? 1022. Okay, 1022. 1022. So this is the smallest number. Okay, and the largest number. Okay, so largest number, we already discussed it. So I will ask that question: what is the smallest number in a 32-bit or a single precision floating point number? So I'm going to give a hint. Let me give you a hint first. Hint, this one here, let's say this color red. Hint, our, what do you call this one here, sorry, where are you, this one here. So what is the representation here? Okay, so let me, where's that one, sorry, where are you, where's my book, this one here. The hint is we have this inequality, where are you, this is negative 126, negative 126 less than or equal to a minus 127, equal to 127. So if you remember it before, you can calculate it this way. Where are you? This one here, this explanation, where are you? This one. Okay, so we'll call this and apply it to the 32-bit floating system or 32-bit floating point representation of a given number. Okay, you can apply this idea. So next is, how about the largest? This one here. The largest is for the double precision. We have x negative 1 to the 0, 1.11 1 times 2 to the 1023. Again, this is equivalent to this one here. This, sorry, where are you, equivalent to this one. Okay, so how to get the largest number in a 32-bit largest number? I am going to ask this question in our, when I'm going to upload this video in the Edpaso. So this is actually a question mark. Okay, So everything is in the hint, okay, in this hint here. So what are other important important facts about the 32-bit and the 64-bit floating point representation of a given number? So maybe I am going to uh, put some comments here in the later part of the discussion. Okay, so anyway, uh, I guess we are now ready to discuss this topic, how to represent the integers in in a computer. Okay, so integer and a real number. So we discussed this before. So how do we represent an integer? Okay, so just relax and please study what I have discussed in this video. Okay, so I'm going to uh, finish the recording, and then in the next video I'm going to discuss on how to represent the integers in a in the computer. Okay, so thank you so much for listening. God bless.